Two cylindrical rods, AB and BC, are welded together and loaded as shown. Knowing the average normal stress should not exceed 175 megapascals in rod AB and 150 megapascals in rod BC, determine the smallest allowable values of D1 and D2. So in this problem, we are going to calculate out what the diameters need to be. First thing that we need to do is we'll draw a free body diagram of this problem, and we will apply our loads to it. And so let's go to draw in some of the forces in the y direction. I have 40 kilonewtons pulling down, I have 30 kilonewtons pulling down here, so if I do a sum of the forces in the y, with upwards being positive, that has to equal 0. I am going to have some force in y here, and we'll call that AY. That's the reaction at A. And if I go and do this, I don't have to write this down, but AY is going to be 70 kilonewtons. So we do have our external force. And so we can write that up here as 70 kilonewtons. So now I've got all the external forces on my object. And so now what I need to do is I need to start taking a look at what internally is going on with the rods. I don't care what's externally going on. Once again, it's all about internal forces. So what do? Well, I'm going to make a cut. So as we know from mechanics, what's going to happen? When is the force going to change in this body? The forces are only going to change internally when an external force is applied. So I will make a cut here and look at what's internally going on, and then that's all going to be the same until this force is put on, and so I will cut here. So let's draw a free body diagram of this part here. Externally, I have 70 kilonewtons on it, and so that means internally I'm going to have to balance that out. And so the internal force there is also going to be 70 kilonewtons, because it has to, no matter what's going on, has to be in a complete state of static equilibrium. So I know the internal force in FAB is going to be 70 kilonewtons. So we'll come back to that. We'll draw the free body diagram up to the second cut here. So I have the large end of the cylinder with 70 kilonewtons there. At the end of this, I have 40 kilonewtons. And then I have the smaller one where I'm making the cut. And since I am making the cut there, I'm going to have to do the same thing and balance everything out. So I have 70 kilonewtons pulling up. I have 40 kilonewtons pulling down. I do my sum of my forces in the y direction on this. So sum of the forces of the y equals 0. And I have 70 kilonewtons going up, minus 40 kilonewtons going down, minus whatever this force in BC is pulling down. That all has to equal 0. So now when I go and do that, my internal force there has to be 30 kilonewtons. Goes 30, 40 to 70, everything balances out. So my force in BC is going to be 30 kilonewtons. So that internal force changes because the external force changed. And so now using that information, we can go and solve our internal equations. So let's get some space here. Let's look at AB. And with AB, once again, I know my internal load, so the force in AB has to be 70 kilonewtons. And I'm just going to go right to my definition of stress. So the stress in AB is going to be equal to the force in AB divided by the area of AB. Now I already know what my allowable stress is, and I know what my force is, so I'm going to rearrange this for my area. And so the area of AB is going to be the force of AB divided by the stress in AB. And I want to bring that down even further, so I know that my diameter is going to be pi over 4. So we'll just invert that, 4 over pi times, let's write this out a little bit more. So D1 And so we still have FAB over stress AB. So area, that's pi over 4 d squared. So if I want to bring the d out, I'm going to have to do the square root of 4 over pi times my load divided by my area, and take the square root of all of that. So 4 times 70 kilonewtons, or 70 e to the 3 newtons, divided by pi times the allowable stress in AB was going to be 175 megapascals, so 175 times 10 to the 6 newton meters squared. Just quickly looking at the units, newtons will cancel, I'll be left with meters squared, but I'm taking the square root of that, which is going to give it to me in meters, so that's all great, that's what I should expect. And if I plug this into my calculator, I'm going to get 22.6 times 10 to the negative third meters, which tells me that D1 is 22.61 millimeters. Any smaller than that, and it will break. It will not pass that allowable stress. Do the same thing with the second one, except the difference is our load is 30 kilonewtons. Actually, let's keep our notation consistent. The force in BC. And so we're going to do the same thing. The stress in BC is equal to the force of BC divided by the area of BC. And we're going to rearrange that equation just like we did for the first one, and we'll just jump right to it. D2 is going to be 4 over pi, force of BC divided by the stress of BC, and we'll take the square root of that. So 4 over pi, force in BC was 30,000 newtons. The allowable stress in BC was 150 megapascals, so 150 times 10 to the 6 newtons per meter squared. Take the square root of that entire thing, and we will get 15.96 times 10 to the negative third meters. And so what does that work out to be? Well, that is 15.96 millimeters. Any smaller than that, and our internal stress will be greater than our allowable stress. And so that's how we can look at stress and calculate out diameters and whatnot. We'll see a lot of problems, especially in the Connect, that are dealing with cylinders like this, where we're having to cut and find out the internal force. Because once again, the internal force is what's most important for stress. So with that, if you have any questions, let me know. Otherwise, I'll see you in the next video.